Here we're going to get into some key math skills, just some important things, and I hope that a lot of this is review, things that you learned in your primary and secondary education, but just in case, we're going to go through it. So for any number that we have, there are place values, and those place values have names, and so we have the thousands place, the hundreds place, the tens place, and the ones place, and I'll add on here, even though they don't say this is a unit. Any measurement we make, and a lot of times measurements that were made for giving you an example problem, those measurements should always have units. There are place values that are higher. We won't see a lot that get higher this year, but they do exist. And of course we can combine those with numbers that are after the decimal as well. And so after the decimal here, we have the ones place, we have the tenths place, which is a fraction, and if you're having to speak it, you have to be careful because tens and tenths sound the same. One of the teachers at my school always says, you make your ugly face, and I will frequently overemphasize that, and so I'll say the tenths and really try to emphasize it because I know it doesn't always come across clearly on a recording. The hundreds place and the thousands place. And again, here we have a unit as well on this. There's a reason for that, and there's a reason why sometimes we'll write numbers after a decimal. Like if I have $3, I can write that down like this, but I can also write that down like this. And in chemistry, a lot of times, we will leave those zeros there. If you measured it to be a 0, then you measure it to be a 0, and we include that. And we'll get into why we do that and how we handle that in calculations in a later topic. Anyway, simple practice problem here, labeling the place values. So this one here is the tens place. This one here is the ones place. This here is the tenths place. And lastly here we have the hundredths place. Most of the time we have a number, it's a positive number, and it's just a number, but it can be written as a plus that number. There are also negative numbers. You won't come across a lot of negative numbers. You can't have like a negative mass of a substance, but there are occasions negative numbers have to be written with a negative sign. It is written like and looks like a minus sign, and mathematically it behaves like a minus sign, but it is technically a negative sign, and there's no way to write that without the sign. With positive numbers, if the plus sign isn't written, it's assumed to be positive. You've learned before your multiplication tables, but when you have negative numbers, if you take a negative times a negative, you end up with a positive answer. And I'm not going to get into the mathematical proof as to why, but you end up with the a positive number. When you multiply two positives, you end up with positives. So two positives, it ends up the same. Two negatives, it ends up being different here. When you have a positive and a negative, or a negative and a positive, when you have one of each and you multiply them, your final answer ends up being negative both times. Same kind of thing happens with division, so I'm not going to spend a lot of time labeling here. Two positives gives you a positive, two negatives gives you a negative. Negative and positive, positive and negative, doesn't matter which order it is going to give you a negative answer. When we are doing addition, we assume that the negative numbers are like a subtraction. And so you've done normal addition, you've probably done addition with negative numbers before, but we treat that negative sign, and so this is the same thing as saying minus 3 minus 4. And so we're wanting to go 4 below minus 3 already. And if it helps you do the number line thing, it's totally fine. I'm not going to care. What I care about is that you're getting to the right answer. And so if you start at negative 3 and you want to go minus, you want to go lower 4, then you end up at negative 7. Totally fine. Should at least label my 0 on the number line there. Like I said, when we're doing addition with negative numbers, then we treat this as if it's a minus sign, and so then we can do that. And then here are a whole bunch of different examples. The big thing I want to point out is that when you have a minus a negative, that double negative there is the same thing as plus a positive, as my math teacher always said, or as just plus. The two negative signs cancel out. And so that's the only oddball thing there. Make sure you take a look at those and understand them. But one thing, you're always allowed to use a calculator with me. And so it does have to be a basic calculator that is not attached to a cell phone or a computer. It has to be a standalone calculator. You will be fine with a scientific calculator. If you have a graphene, they're a little bit more powerful, and they might help you if you have to take other classes, or even be required if you have to take other classes. So make sure you know that. If you don't know how to use your calculator, they do come with manuals. You can ask me. I'll try to walk you through it. I will say on a graphing calculator, frequently instead of equals, they will have just a enter button in place of that for kind of inputting what you want to do, and then it will give you the output, which is your answer. Be careful. You have to use a sign button. Sometimes it's just the negative sign button, but you have to use that instead of a subtraction sign when wanting to write a negative number. It throws the calculator for a loop if you mix those two. This gets into how to type it into a calculator. If it should be similar on your calculator, make sure you know how to use your calculator. But because each calculator is a little different, I'm not going to spend time on this going through it. Percentages. Percentages trip people up for some reason. What I want to point out here, though, per cent. You're familiar with both of those parts. So per, for example, you've heard of miles per hour, which we abbreviate as mph. But mathematically, that is miles per, it's a division sign there, hour. So the first thing we have here is that we're dividing something. Cent you're familiar with. You've, of course, heard it with just a penny, and you know that 1 cent is that part of a dollar. It's essentially a percentage. You're taking a $1 and per cent. Cent means 100. You're dividing it by 100. What's more, you've also heard that prefix cent in a word like century. And you know that century is 100 years. And so cent simply means 100 here. We just combine the two, and a lot of times we don't take the time to break down the word, and then you just have a math teacher tell you to do this, and they don't really explain why. But percentages are ways to kind of give us a comparison. And a lot of times what happens is we end up with tiny numbers. And so if you do this calculation here, you end up with a tiny number of 596. And what we mean by that is when you have a pill, and I mentioned this in an earlier section, when you have a pill, it's made up of a active ingredient, which is a tiny piece of it, and then some filler stuff. And to be honest, this sounds kind of low for aspirin. A half a gram tablet would be really tiny. They're probably a gram or two, most of them. And so then your percentage would be even lower, it turns out. But we don't have to worry about that. We can work with these numbers. But you end up with 0.956 here. And what we're saying is that out of the whole thing, we have 0.596 of it. And that's not as clear as doing a percentage here. And so what we could do is we could turn it into a percent. And the way we do that is we multiply it by 100. And when we multiply it by 100, we're actually multiplying both the numerator and the denominator by 100. Then we end up with 59.6 over 100. And we can talk about how it's now 59% or 60%, which maybe makes a little bit more sense, that if we broke it into 100 parts, 60 of them are the medicine. Or that you can imagine a pie chart where we have your tablet, and now we can say a little bit more than half is the medicine, and the rest is not. And it's maybe just a little bit easier to visualize. You'll notice that we don't write this as 59.6 over 100. We instead 59.6%. Well, that percent means per divided by cent, 100. In fact, this isn't exactly why that's our percent symbol, but you can imagine we take the 1 and we write the zeros on either side of it. It's not why that's a symbol. That slash is actually for the division, and the zeros are just what we chose, or the O's were just what we chose for that. When we have something that is a percentage, then what we mean is it's that many out of 100. Of course, when it comes to chemistry, we may have, when you have atoms are so tiny that we will have literally a trillion of them maybe. And there it is no longer reasonable to think about it in terms of 100, but we can pretend and we can use percentages to help us along the way. One downside is using percentage function on a lot of calculators is difficult, and so a lot of times you have to do the reverse process. Mathematically, it is almost easier to do the percent, take these divided by 100 to get the decimal version of them. I think of a lot of things in terms of money. Percentages are very much one of those. I look at this and I see 50 cents, and I think 50 cents is $0.50. And a lot of times we'll write that leading zero in there. But that's the same as dividing it by 100. A lot of times, teachers will instead tell you, well, you find the decimal and you move the decimal to this way when you're turning a percent into a number. And when you have a number like, let's say, 25 cents that you want to turn into your percentage, then you move the decimal the opposite way. And what I find is that students forget which way to send the decimal. If you think of percent as per 100, as it actually is, then you're dividing by 100. Well, if I take a number and divide it by 100, I'm going to be getting a smaller number. And so if I'm going from a percentage to a number, it's going to give me a decimal. And then I can remember that the other direction is opposite. And I'm multiplying it by 100. To me, that's how I think through it. Whatever works for you. And if you can figure out how to use the percent function on your calculator, do. Before we start this one, I want to point out for those of you who followed along with the original PowerPoint slides, there are times like this where they will work through step by step a math concept, and I will remove those and just work through it on my own like this. I think hearing the process makes more sense. When it comes to solving equations, we do sometimes have to do a little bit of algebra here. It's fairly basic algebra and it doesn't come up a ton, but for example, here we have 2x plus 8 equals 14, and the first thing to do is to get like things on the same side. That is to get all of our x's on one side and all of our numbers on the other side. And there's what's called the golden rule in algebra. You do to one side what you do to the other side. So to get rid of this 8, the simplest way to do that is to subtract 8. Well, if I subtract 8 from the left-hand side here, then I have to subtract 8 from the right-hand side over here. And so now, when I subtract that 8, it's going to cancel out, and we're going to be left with 2x. The plus sign doesn't matter because that 8 is gone. It's a 0 now, and 2x plus 0 is still 0. So I'm just going to leave it as 2x is equal to, and 14 minus 8 is 6. Hopefully you can do that in your head, but you're always welcome a calculator. And once you've taken care of rearranging the addition stuff, then you can rearrange the multiply divide stuff. And so we have 2x on this side and 6 on that side, and so we need to get the x by itself still. It's what we're trying to solve for, the unknown variable. And so we're going to divide both sides by 2. When we do that, these 2's are going to be canceled out. We're going to be left with x on that side, and 6 divided by 2 gives us 3. And so then our answer is 3. Something that I never did in my primary, secondary school, but did a lot in college because unfortunately these classes cost money, is check your answer. I would encourage you, if you have time left on a test, don't just say, oh, I'm done, I get a break. Go through and check your answer. Maybe I don't do that on every homework assignment, but boy, I would go through test 2 and 3 times if time allowed. Now, in my higher up classes, I was lucky to get through the test one time and wasn't able to take the time to check my answer. But here, you hopefully will have time. Most students don't take the whole time taking their test, and I'm sure plenty of them don't check your answer. But what you can do is you can take your answer here and plug it back into the original equation. So the original equation was 2x plus 8 is equal to 14. Well, if x is 3, then this statement should still be true. So what we're going to do is we're going to replace x with 3. And when you have an x by a 2 like that, it means that you're multiplying them. So 2 times 3 plus 8 is equal to 14. Now, some of you may be able to jump ahead in your head, but I'm going to go ahead and baby step it here. So 2 times 3 is 6 plus 8 is equal to 14. And 6 plus 8 is 14. So 14 is equal to 14. Therefore, and this little 3 dot thing is the math symbol for therefore, x is equal to 3. We have checked our answer. We are sure that is correct. As a side note for me, if you show your work like this, I can give partial credit when you're doing calculations. If you just do a calculation and give me an answer and I don't see any work, I unfortunately can't do any partial credit. And calculations frequently are worth a lot of points, and I like to be sympathetic. I understand that math mistakes happen. This is more class over chemistry than it is over math. Certainly math is a phenomenal tool for chemistry and we use it a lot, but if you make a simple math mistake, I'm willing to give you partial credit, but you've got to show me your work. If you don't show me details like this, or if I can't understand your work, or if your handwriting's sloppier than mine and I can't read it, I unfortunately can't do partial credit. So please do show me your work, unless you've gone through and you've checked every answer and you are confident that those answers are correct. But even then, show me your work just in case. And over here, they have a learning check, but this one here, they want you to solve this equation, and there's no numbers. I have to be honest, anytime I had the chance, even through most of my undergrad, to plug in numbers and do the math with numbers instead of with variables, I did. I hate doing math with letters. Now, what we have going on here is this is actually an equation you'll see when we get to the last gas laws. This is the Boyle's law equation, and what it's saying is that pressure times volume is equal to pressure times volume. And so this is why you may fill up your car tires and then later on they've shrunk because the air pressure or the temperature, which is more likely in that case, has changed, and now they don't have the same size. And so you have two different pressures and two different volumes, but the total product of those two has to be equal. Or bubble wrap. Everyone loves to pop bubble wrap. You increase the pressure on that, and when you push on that bubble, you're squishing the air and you're decreasing the volume. You're increasing the pressure on it and decreasing the volume on it. That's what this one is. Anyway, we can do the algebra here to rearrange and solve for P1, but if normally what will happen is you'll be given a problem where you'll be told the original pressure and volume are such and such. And so you'll be given those two, and then you might be given the after volume and asked to solve for the after pressure. In this case, we're asked to solve for this one here, so that's what we're going to rearrange to solve for. So to get P1 alone, we're going to have to divide both sides by V1. When we do that, over here, the V1s are going to cancel out, and we're going to be left with P1. We've already got P1 alone. This one's only going to take us one step to do. Is equal to P2 times V2. Personally, I like to put the dot in there just to remind myself I'm multiplying, and to kind of help me ignore the two subscripts there. And then we're going to divide that by V1. And so then that is our answer here. Now, substituting this one in and solving for it and proving that this is correct is a little ugly, but I'm going to go ahead and do it just to show you that you can. So if this is correct, if P1 is equal to that, then if we start with the original equation again, P1 times V1 is equal to P2 times V2. Well, I'm still going to have P2 times V2 over on this side, and I'm going to have V1 over on this side, but I am going to be substituting this for P1 over here. And so we have P2 times V2 divided by V1. Well, now that we have this P1 is times the V1, so this whole thing is times the P1, and you'll notice here that the V1s are going to cancel out with one another, and we're going to be left with P2 V2 is equal to, and those two are the same thing, so we know our answer is correct. A lot of times when we're looking at data, graphs will be helpful to look at. This is a similar idea to what I was just describing, that as you change the temperature, you can change the volume, and so you fill up your car tires on a hot day, and then on a cold day, you'll notice they've shrunk and you've got to fill them up again. That is another gas law relationship, happens to be called Charles's law, which we'll get to later in the course. Reading a graph can be helpful for showing relationships that are there. So this data has been plotted for us already. In labs, you may have to graph the data yourself, but just want to go through some of the basics. So first off, over here, we tend to use a linear scale. That is, we're counting up by a regular number. Over here, they're counting up by +2 each time.
If you want to come up with a mathematical equation for this one, you really have to take this all the way down to the zero, and doing the zigzaggy thing is frowned on because of that. But if we're not coming up with a math equation, we don't have to worry about that. And there are some ways around it, and I am totally fine if you choose to do graphs on the computer and let the computer do some of the graphing for you. Down here, they're counting by 20s, and nothing says that you have to count by the same number on both sides. You just have to be careful when you go to do the math if you're trying to find something like the slope of that line, because a lot of times that slope is our relationship. Anyway, when it comes to having a graph, we have down here on the x-axis, the horizontal axis, one variable, in this case the temperature. And usually this is your independent variable. Now, we didn't mention that when going through the scientific method, but independent variable is the thing that I am testing. It's the thing that I, the experimenter, or of course any other experimenter out there, but the thing that I, the experimenter, am changing. So I have a balloon and I change the temperature of the balloon. Well, when that happens, when I change the temperature of the balloon, the volume changes. So the volume here is our dependent variable. It is what depends on the independent variable. I mentioned earlier the pendulum experiment. We talked about me changing the length of the string, or the angle that I pull it back at, or how heavy the weight down here at the bottom is. Those are all things that I am changing. Those are our independent variables. Our dependent variable is how quickly it goes tick-tock, how quickly it swings back and forth. It turns out of all of those, only one of them changes it. It unfortunately doesn't give you a nice, neat, straight line relationship. The other two, they give you a flat line, which means it doesn't matter what change you make, it gives you the same period, the same tick-tock each time. And so there is not a relationship between those two variables, those two things that I am testing. In addition to that, I want to point out here that over here we have the y-axis, the vertical axis. Over here we have the x-axis, the horizontal axis. And those are just kind of standard math terms. Frequently, when we have equations, we're solving for x. There's an equation for our line, and if we need it later in the course, we'll get into that. From there, the other thing I want to point out, or another thing I want to point out, is not only do we have labels here, but we have units. And then, not only that, we have a title. And the title is always independent versus dependent, or y versus x. And very rarely will we do anything that is not a line graph. And technically speaking, other things like a bar graph are really bar charts, but you don't get the same mathematical relationships out of them, and so they are usually not useful. It's not to say they're never useful, it's just not usually the case. Almost always we do line graphs. The other thing we tend to do is scatter graphs, where we plot the dots and then we draw in what's called a line of best fit. If the dots look to be in a straight line, then great, we can connect the dots with a straight line. But when you're doing this in a lab, you're going to have chaotic data that might be in a straight line, but because you made measurement mistakes, or because the temperature of the room changed while you're doing the lab because HVAC kicked on or whatever it is, you don't end up with a perfectly straight line. Then we have what's called a line of best fit that goes through most of the data and is our best estimate of what was going on, realizing that because I spilled a little bit of chemical, or because the temperature changed, or because I would never make a mistake, but human error from my lab partner screws things up. Our data isn't on a perfect line like this, and that's okay. As a side note, this is supposed to be a straight line. It's just the difficulties of drawing freehand here. Now, the next slide and the slide after that get into all of that. And I'm not going to take the time to read all those. The one thing I will say is not only is there a relationship here, but we have what's called a direct relationship. When we have a direct relationship, as one goes up, the other goes up. As the temperature increases, as the temperature gets higher, the volume gets higher. That is a direct relationship. Indirect, as one goes up, the other goes down. Turns out you'll get a negatively sloped line when you do that. And it turns out that's vice versa as well for both of these. For a direct relationship, if it goes down, the other goes down. And on this one, if the first one goes down, then the second one goes up. Direct, they're going in the same direction. Indirect, they're going in opposite directions. And that finishes this section.